So hi again, everyone. Yes, this is another talk that I'll be mentioning very later, of course. And also, I can finally tell you what I actually do. So you all know who I am by night. By night, I'm the content manager for the RISC-V Foundation. But by day, I run a company called Antmicro, and it's fun to work there because we get to work with RISC-V and simulation, all sorts of other stuff. So I'll talk a little bit about kind of our framework and how we think what happened with RISC-V has been very awesome, and we think is very tangential to what we want to achieve. About Antmicro itself, a little bit. We were founded in Poznań, which is like 3.5 hours away from here, in 2009, and Renode was actually started almost immediately in 2010. We'd been dabbling in the open FPGA, open IP, the ORConf kind of ecosystem since almost the same time. And we have an office in Sweden. We're opening another one in Wrocław very soon. What we actually do is like project services for building software-driven products, especially for like early adopters of technologies, which typically means early adopters of new open source technologies or somehow related to open source. We do things like drones and medical systems, aerospace, robotics. We don't really care what it is as long as it's using open source and it's cool. We're members of a few organizations. We're not a corporate member of FOSSI Foundation because there is no corporate members of the FOSSI Foundation, but of course, if there were, we definitely would be. For the RISC-V Foundation, we're also a platinum member, and we also recently joined Zephyr and Linux because we use them a lot, so we thought, yeah, it makes sense. And I'll be repeating that a lot. We're very kind of software-driven, and we see that a lot of innovation can be done in all sorts of tool chains and workflows by introducing a software-driven mindset. I know the software guys are kind of the outcasts here, but yeah, unfortunately, I have to listen through my software-driven stuff here. We think that there's a lot of innovation to be done in the workflows, and we've been very, very happy to see the recent kind of stuff happening, in the open FPGA tooling. Really great talks today by Clifford, by Tim, and David. So overall, we think there's a lot of good momentum there, and we also want to talk about a tool that we think could kind of help here. It's called Renode. It has a website and a logo and everything, but it's really an open source tool that we built because we thought we needed it, and then it turned out that more people needed it, so we open sourced it. Why did we do it? Well, I mean, it's been our own experience throughout the years that hardware is kind of hard to work with. It's very, waterfall style. You first build the hardware, wait for it to be complete, then do stuff. Even if you have the hardware, you end up kind of being very much slower than all the other people. So with physical stuff, even though it's kind of great and it's awesome to have LEDs blinking, if things are not working and the LEDs are not blinking, you don't know what's going on. So especially when the systems get more complex, it starts being very, very hard to debug with printfs and so on. So we thought that this kind of workflow is broken and kind of stuck somewhere in the 1990s. And when we started Renode, or what was to become Renode later, we thought, well, there has to be, something has to be done, and we can do something. So we ended up building a open source instruction set simulator that has also a multi-layered framework for other things on top. So we're basically trying to build in flexibility into this. So our main aim was to kind of make it a very open and flexible tool that you can integrate with lots of stuff and change as you wanted. We are software agnostic. It means that if you want to simulate your software, you won't have to recompile it against Renode. It'll just be like if you want to run on an STM32 board, you'll just build your binary as normal and just run it. If you want to run it on a RISC-V thing, again, just compile it as you would normally, but use this instead of the real hardware. Our target is to mimic entire boards and even entire multi-node systems. So it's not just focused on one CPU or something. It's actually enabling you to build a complex system of multiple boards. I'll talk more about that later. And it's also very scriptable. We have like APIs for everything because we thought that was very useful as we go forward, as things become more complex. You want to do things that we didn't expect, like back in 2010, for example. So we ended up building something which we thought that hopefully it would cater for the future very well. Our cores, like the simulation of the cores themselves, is in C for speed, but actually peripheral models and everything else we actually can do in higher-level languages, including Python, which seems to be a very controversial thing around here. Some quotes, what people have said, it's kind of interesting because we hadn't said that ourselves and we were thinking about our framework like that, but people have said it's QEMU on steroids, or that's a Docker for embedded systems. You can actually run Renode in Docker quite easily, so that will be very meta. Anyway, what we do is kind of try to look at this from a broader perspective, and we don't only like simulate what many people do, like with core and CPU only. We want to do entire SoCs or even boards and systems of devices, right? So we see this as just a layers on layers of building blocks. And if you think about it as Lego, it kind of makes sense. If we look at like the first layer, so if you have system on chips, typically they're composed of like some cores and some IPs that you connect together. And of course, internally it's kind of complicated. But from a software designer's perspective, what he's seeing is like he has the CPU that executes the code, and then there's those peripherals that he interfaces with, some drivers that they're writing, and so on. So different kinds of SoCs have different blocks, and those blocks tend to be reused a lot, like a lot. Throughout the years, we've found that, say a certain Ethernet IP can be used across, things like Cortex-A, for example, Zinc, and then the same Ethernet controller will be used in, for example, a Cortex M7 from Atmel, and also the Hive Unleashed, right? So you'll be having in completely different systems, you'll be having the same IPs, only arranged differently, perhaps a bit changed, but from a software guy's perspective, these kind of overlaps are kind of interesting because you can see, okay, if it overlaps, why do I have to redo it over and over again? Why don't I kind of reuse all this stuff? Then as you go to like level above, if you see the whole device, actually what we wanted to do is to not only simulate a CPU or a SoC, but also to be able to simulate like a button or a LED or a LCD. Generally speaking, input-outputs or sensors, for example, is a good thing to mention. So if people are building their software, they should be able to kind of test it in its entirety. If the software is dependent on some external stuff going on, we also want to enable that. And as you go to a complex system, you might have sensor nodes connected to a gateway or this kind of setup, or even there's sometimes boards with multiple modules on them. We also want to be able to do this because why not? If there's like two boards connected over SPI, why wouldn't you want to kind of simulate that SPI connection as well and just make it work in one simulated world? The kind of platform support that we have today is, of course, it doesn't say very much because it's just a lot of logos, but it's kind of telling a little bit about our history because these are platforms we've been working with, like in our commercial project-oriented leg. A lot of that is like Cortex-M style stuff, but there's also Zinc, and that's kind of stemming from our FPGA interests. And you can see a pattern emerging here in this column, there's some RISC-V related stuff, and that's what I wanted to talk about specifically today. We think that, RISC-V makes things a lot easier in many respects. And the fact that you have a standardized ISA that kind of is open, provides you an open spec, of course, makes it just easier to simulate it, easier to work with it, easier to contribute and talk to people and so on. So, and also it's been encouraging a lot of people to start reusing stuff, not only in the course, but also to talk about open IPs and reuse in the IP ecosystem. And even though the ecosystem was a bit different before, the reuse was there was a lot of it. We kind of predict that there's going to be more, and we're happy because the more people reuse stuff, the easier it is for us to model it. And as I said, flexibility is very important for us. So basically, again, this building block design is what we think will kind of going forward make things much easier. And how we combine things together is not by code, but we basically have a format that's just text-based that enables you to pull things together and just make them work. So I'll give you an example. This is one of our files for a Mi5 platform. It's a RISC-V platform, and to combine like a CPU, an interrupt controller, and UART, so minimum basic platform to run something simple, you only need like, what, 9 lines, right? And we just kind of made up a YAML-like format to be able to put things together in a very succinct way, so that if you decide, okay, now I'm going to have 2 cores, well, just add 3 lines, right? And now I'm going to kind of put something on a different bus address. Sure, that's just a very minor change. And we made this kind of format like human readable and modular and extendable. It's kind of what we experienced ourselves, how you end up working with the SoC platforms that you're doing. So it's not about the format itself, of course. If it was just kind of a format, that wouldn't warrant the whole framework. There's a lot to it that's kind of enhancing the experience. There's a lot of capability to do plugins, and the plugins can really be just runtime loaded things. Don't have to be really compiled in. We have interfaces that we inherit from, so that if you write something that's very similar to something else, probably the best way to do it is to abstract it out and have an interface for it. We can have, again, extensions of various sorts, again, just kind of injected in runtime. Peripherals, we can stub them, we can write them in Python. If you don't want to kind of model an entire IP, you can just provide a small Python script that returns 1, for example. If your IP kind of is supposed to return 1 in a certain context, just write a Python line. We have a very flexible like logging system with tagging and yeah, the Python scripting I already mentioned. There's an example that we had recently, so I thought it would be interesting to mention it. Basically, what if you have like something that's very similar to something you already have, but you needed one minor change to actually enable it. So we had this with VxWorks5 that we were using, and we needed some minor change in how the CSRs were being handled. And so basically you grab an existing CPU model you inherit from, and then you just override the stuff that you need. So kind of building this variant only needed a few lines of code, and the rest was the same as a pre-existing model we had built before. So this is kind of an example of the reusability that this enables. I'll also talk a little bit about a board that probably some of you already know. It's the High-5 Unleashed, and it's been kind of the de facto standard platform for trying to run Linux in RISC-V. Hopefully, of course, soon enough, it's not going to be the only platform you can do it on. But right now, it's kind of the standard. So when we were kind of implementing this, because we have support for this platform in Renode, and when we started doing it, it was like, okay, 64-bit RISC-V, that's kind of twice the fun as implementing the 32-bit version. So we wanted to do a demo for the Barcelona RISC-V workshop, and we thought, well, okay, so if we can do 2, then it means like it's 4 times the fun. So yeah, we went on and simulated 2 of them. And remember, these are running in the same like time domain. They're kind of we have a virtual time concept, which kind of means that we're not really running them separately. They're both running the same simulation. But then we thought, okay, so if we can do 2, then let's just do 2, and then 2 other ones that are 32 bits, and run 2 different operating systems on each of those. And basically, we expanded the demo to feature like, lots of things. And it still works, right? Because like of the flexibility. So essentially, sorry about this, but the lighting is not very perfect for showing this kind of slides. What we see here is basically a lot of, I think it's 6 machines altogether, connected. That's the console, that's a log. But the 6 machines connected, they're basically communicating over serial ports. And we're setting and reading virtual GPO values, like driving LEDs and buttons. And in the end, we're kind of reading the values there in Linux. That's one of the things we're running. The one is here, one is there. And we have toggled the states of LEDs, and we've seen that they actually changed. So it was kind of interesting to see like, so many different things in one simulation, because we could actually test like interoperability between different things that people don't typically actually do, right? People typically focus on one platform. We can actually just run multiple and connect them together. Yeah, I won't talk much about Renode as such, I have some slides, but I'll just breeze through them. So we do have like this full determinism, and I've talked about most of the other stuff as well. We integrate with like GDB, Eclipse, Robot, Wireshark, and some CI frameworks like Jenkins or GitLab CI. We collaborate with a few OSs. The most interesting thing is Zephyr, because in Zephyr we also maintain RISC-V, so it's kind of a cool collaboration. Yeah, so these are kind of the obvious things. I can mention one example. So that's like a GUI that we've been developing, and we have a CI setup for it with the simulator, with Renode in the loop, and we can basically, for example, extract images while when the UI is rendering. Basically, you extract an image of every few frames, put it together into one big artifact, and you can actually compare if the result you're getting is okay. So you can do a lot of cool tricks. Yeah, that's an example of the testing that we have. So Robots is like a Python-based test framework, and you can get a suite of tests running and see if everything's okay. The multi-node capability means that you can do like virtual networks with kind of wireless stuff going on, connect Wireshark, and see the packets flying. And we can also simulate like sensors, which means that we can also input temperatures and see what happens if, say, there's 37 degrees outside. And I don't mean, of course, physical simulation. There's nothing of that sort. It's pretty simplistic. But it kind of enables you to kind of input some data and see what will happen to your system. And yeah, there's some collaboration features too. The one case I wanted to mention quickly is our collaboration with Dover. These guys have been developing like security IP. They're also a RISC-V member. And that's the cool thing, right? In the RISC-V Foundation, we've been able to collaborate with multiple people because they're all interested in driving this open ecosystem. And these guys have been building like a security platform that's kind of hardware, software based. And so Renode is being used both internally and also for their customers. So they deliver to their customers, also an XP, for example. And we made some improvements in Renode for them. And they're using it, and it's showing how well you can kind of use Renode in unexpected circumstances. So they're using it for like hardware, software code development, which wasn't a primary use case initially. But it turns out that since the framework's flexible, we can do it as well. And now Dover and all of their customers are using Renode for like trying out different security scenarios with IP in development that is kind of being tested with Renode. Microsemi I've mentioned, we also did support for their Mi5 stuff, which means that through their soft console Eclipse-based IDE, they'll have lots of their customers actually using it because that's going to be their default workflow for this. So it's coming out from being a niche thing or a thing that's being used internally in organizations to something that the big, traditionally very conservative silicon vendors will be pushing to their unsuspecting customers. Yeah, so hopefully we can kind of force some people to use more open source. There is documentation. It's always too little. You can help. So I encourage you to see it and suggest changes. There's lots of future ideas, of course. And yeah, I told you I'd mention Verilator, so here goes. Certainly one of cool ideas that we've been having is like, what if you could actually simulate stuff in Verilog and just connect it to Renode? That's a cool idea. We want to think about it. We want to kind of see if that's possible. So basically, you could expedite, most of your design into a like functional emulation, so that you wouldn't have to care about it. You would save a lot of resources and focus on verilating the stuff that you really care about. So it sounds great. Remember about the soft CPU contest, of course. If you want to participate, come to me. That's one announcement. And another quick announcement: we're also launching a labs concept, which is going to be a space where people can develop open source stuff using stuff like SymbiFlow and Renode and OpenRISC and RISC-V, whatever you want. The important thing is like we're building it as a space close to our headquarters in Poznan. We want to kind of build on the concept in the future, and we want to have people working with those open source technologies, not necessarily as part of Antmicro. So I mean, the people in Antmicro are working with open source, but we want to have young people doing stuff that they want to do, but we want to direct them specifically to use open source. And that's a hard requirement, right? So you can't come into the lab and do something proprietary. Yeah, so there's a website, and we're looking for like lab rats, labsters. We're thinking of a name. So if you have a name suggestion, tell us. Currently, it's looking for members, right? Thanks.
Thank you very much.
This looks excellent, thank you. I'm going to ask on behalf of my rest of my hardware colleagues and people I'm going to talk to, is it cycle accurate?
No. This is instruction set simulation, so I did mention it in the slide, but so it's actually not the same thing as like cycle accurate simulations, and its purpose is different, right? So its purpose to be a fast simulator for software development, which is, of course, many use cases, not all of the use cases, but it's kind of meant to fill a certain segment. But we definitely don't want to target like everything and say, you know, everyone in the world is going to use. That's why I'm saying I'm the software guy coming from the software world. I know many of you will probably not use Renode, but we still think it's valuable to discuss it here.
I think it's still be very useful anyway for our software brethren to also have that access.
We have other questions. Sorry.
Yeah, I was just curious, you know, for, I don't know, say a 4-core machine or something like that, what sort of performance would you expect?
So, I mean, we're talking running Linux in several seconds, right? Or like basically, we're trying to replicate it fast enough so that you can kind of have the native experience, right? We actually have a concept of virtual time, so it's not exactly.
I mean, is it like equivalent to QEMU or?
Yeah, yeah, that would be the level of speed.
If there are no other questions, let's thank the speaker again.